So we'll be talking about embedded Java, but really small embedded Java solutions that can run on very low-end processors, so that you can embed Java almost everywhere you want, as long as you need some data processing. So I'm Regis. My company is IS2T. This is a French company. The founder of the company, Fred River, comes from IBM, and he was involved in the Gen9 VM design. And he also wrote a big part of the Eclipse Java compiler. And on my side, I come from more software and embedded software area. And we founded the company in 2005 to provide low-end and low-cost solution for embedded Java. Anybody is aware about what is embedded systems? Yeah? Okay, so here is a quick map of what are embedded systems and the CPU cost or price. So you can see on the right side that the more than $25 that are high-end tablets and high-end smartphones and so on is not as much as low-end microprocessors, $1 or $2 that are used in washing machine, coffee machines, and so on. And more of these devices are increasing in memory, so software complexity, and the actual language, which is usually C code, is not adapted now to the challenges they have to solve for data management, GUI design, and so on. And this is where we want to bring Java on top of the traditional gateways and other systems. So this is where we are. So we deal with edge devices if we are talking about IoT systems. So you have edge devices with microcontrollers and small processors, roughly less than $15 for the cost. And also gateways. In gateways, you might have very high-end gateways, but also small gateways that you can connect to a higher-end gateway. So like home automation gateways to deal with some edge devices. And these gateways, the bill of material cost can be $15 overall. So you cannot afford an Android or Linux based station, even a Raspberry Pi. If you are looking at home automation, you need something that is really reliable with a good manufacturing process and so on. So it's not a pure consumer market. And the idea is to provide Java because we want to provide portability of all applications and help customers to decouple the software from the hardware, which is quite natural on C world, on PC world now. But in the embedded system, usually the code is so optimized due to cost issues that the software is tightly coupled to this hardware. So when the developers want to get some innovation from the electronic manufacturers to get a new function on the microcontrollers, on the microprocessors, they cannot get it, they cannot use it because there are so much changes on the software that the cost to get access to that electronic innovation is too high. Okay, so what we want to help our customers is to decouple the software and the hardware so that one day if they change of microprocessors to get some kind of innovation, they don't touch, they don't change the software, and we lower the cost, development cost of embedded systems then. Another thing that is changing also is the embedded market maturity. If you go back 30 years ago, people in the embedded system would have designed their own CPU and their own micros. Now they buy the micros. 20 years ago, everybody was doing his own firmware, driver, its own operating system. Now most of them either they buy or they get open source, but they not make themselves the thing. On bigger system like PC or smartphones, nobody would reinvent or redo just for fun an Android system. Okay, so you buy. And this is what's happening in the embedded world also. The platform, the application platform, the execution platform is now mature enough to be bought outside the company instead of making their own application platforms to develop their own platform. And this is where we are now, where we stand. The market is mature enough to let players like IS2T to provide embedded Java platforms that are usually bought for larger systems. And this is what we offer. So we have three kinds of platforms, of Java platforms. They are all compliant to the Java standard, right? But they have some kind of different implementations according to the market they are targeting. So the first one is Embedded Device Edition. It's general purpose embedded Java platform. The second one is Hardware as a Service. This is typically what is used in gateways, robots, to share applications mainly based on the OSGi framework. Everybody knows about OSGi? Okay, so we will have a look on this later on. And a more specific platform, we managed to get a Java virtual machine deterministic. You know, in the JVM, you have a garbage collecting system, so you have lots of automated systems, and that prevents the software processor to behave like a deterministic system. And we managed to get it deterministic, meaning that now we can offer Java in safety critical systems like avionics, transportation, and so on. Most of our platforms are now portable on a wide range of a hardware environment. So microcontrollers mean it's a processor plus RAM plus ROM inside on the same silicon. And usually the maximum price is about $5. On microprocessors, so it's based on Linux, VxWorks, Integrity, PikeOS for safety critical systems. And we also offer a port on Android and iOS, and also as an applet that can be embedded in the HTML page and can be executed by your internet browser. So if you use the embedded edition, then if you write, say, a graphical user interface, you'll be able to run this interface on a small microprocessor, a microcontroller. You'll be able to run it on Linux. That means if you choose a microcontroller or a microprocessor with a different operating system, you keep the same software, right? And you can also export that GUI on Android and iOS, and you can export that GUI on the web without changing anything. Okay? So here is an example here. So this is a pure Java program designed with Eclipse. And you see four demonstrations. The first one on the top left, this is our simulation system. So it's in Eclipse, so you can see a Windows window. And we have a simulation system. You can build your own front panel of your embedded device, and you can run your software to test it, to prototype it. Here on the right hand, we hacked the first version of Sony Watch, the smartwatch, and we bring the JVM on top of it, and then the same software can run on the smartwatch. On the left, of course, we can export that application on the smartphone like Android, and on the right, on another microcontroller, just a very small and not expensive controller. On the Sony Watch, it's based on a microcontroller as well, built from STMicroelectronics. The main challenge in the embedded world is that you have many architectures, because it's cost-constrained environment, so you don't have to choose between Intel and AMD. You have to choose around a myriad of microcontrollers and processors. And then the main issue for the software editor like IS2T is to be able to provide a wide range of GVMs that complies to the same specifications, but that are implemented on different hardware, right? And of course, if it takes 1.5 years to design a GVM for a controller, then you are not fast enough to be able to provide on the market all the GVMs that your customers would provide. So this is our job. Make Java virtual machines, even specific ones, very quickly. And we managed to get these GVMs available as a standard Java VM, but with a high-speed execution, almost as fast as C code execution, with determinism, tiny footprint. We'll see the footprint afterwards. And of course, very easy to interface to C code, because most of our customers in the embedded world, they've been developing applications with C code for 20 years, and they wouldn't put in the bin everything, right? So the idea is to say, C is perfect, now your application is getting more complex, then choose Java, but keep your legacy code you invested in, and keep going with the two technologies to get the best of the two technologies. Here is an example on STMicroelectronics microcontrollers. So the microcontroller here is about 512 kilobyte flash. So you only have 512 kilobyte for everything, for the program, and 128 kilobyte for RAM. And this is a washing machine GUI. And so we use standard Java libraries for the graphics and for the object management. And you can see that the virtual machine size is about 28K. Okay? If I add the libraries, the graphics, the communication libraries, and all the drivers, the floating point unit, and so on, it's about 130 kilobytes. So all included, the Java platform, using a graphical library, like you saw on the video, it's about 150 kilobytes. And you've got everything included with the standard Java platform. Of course, in such applications, you have to store graphics like icons and so on. So the graphical resources takes quite a lot of room. And the application itself is about 30K, 34K. On the RAM size, the GVM just needs less than 1 kilobyte to keep alive and to make its job. Okay, and then you of course you use a multi-threaded applications, so you need native stacks for the threads and so on. And the Java heap is about 13 kilobyte, so very small. Okay. So that's examples of this kind of HMI we can provide. This is a medical, on the left there is a medical application. On the top it's a home automation system for smart energy monitoring, and some demos with generic rendering. All based on STMicroelectronics processors. The thing that is also interesting, just a word about ST. So we partnered with STMicroelectronics because our business model is based on a royalty payment. So each time you deploy Java, you need to pay a royalty. For your information, to get that technology not as a rocket science but as an industrial delivered technology, it cost about 10 million euros investment. So we have to get back this money with royalties. And when you buy microcontrollers from ST, you buy directly from them the royalty, because the microprocessors they sell are Java ready. They already include the Java technology inside the chip. Meaning that when you buy from ST to make your embedded system, you have nothing to do with IS2T. You just buy from ST, and this is a one-shop stop. Okay, so now let's have a look at the more technical things. we will have a look at the embedded edition, how you can integrate Java to an existing C code and C application. And the second part will be about the hardware as a service, how you can handle an ecosystem like Android on a small microcontroller, right? So let's have a look at the MicroEJ. MicroEJ is our solution for designing Java. So it's both SDK and Java platforms. So if you look at here, you have some hardware here. Then an operating system, if any, could be yours, could be any kind of operating system, and your drivers here, the BSP. And on top of it, you will bring the Java virtual machine with a couple of different libraries. So the well-known embedded libraries is CLDC, but we also provide a library called EDC as a profile, which is compatible to the Java 8 standard. We provide some mechanism to interface to C code. This is what we see. And then on top of this, you have a bunch of dedicated libraries like Graphical User Interface, Internet of Things for protocol management, and so on. So the MicroEJ SDK is based on Eclipse because we are very close to Eclipse world. So this SDK allows you two things. First, to build your Java platform on your own, okay? And then to extend this Java platform with your native code, because you might have special sensors or you might have special things to integrate and to be visible from the Java world. And then it will allow you also to write your Java code as usual, and then to test it in a simulation environment, and then to deploy the Java code and everything in the microcontroller as well. So first, what you have to do is to include the JVM in your existing system. So imagine you have a hardware with some kind of RTOS, very simple, could be a 10K RTOS, and you already have some native tasks that are your C tasks. That's your existing application, right? If you want to bring Java, then you just create a new task. And then you launch the Java virtual machine inside that task, right? And then when the Java virtual machine will start the Java code execution, and it will create new threads in orange here. And these new threads will be scheduled by the Java virtual machine, because the JVM is in RTOS. There is a scheduler inside the JVM. That's part of the specification. It's a multi-threaded processor. So this is very simple. It's not a black box, very clear situation. You've got one side your C code. There is a special side with your Java code that is executed in a single task of your RTOS. This integration has many advantages. It's pretty simple. Usually for a guy who doesn't know about our technology, it takes about 2-3 days to get the JVM running in the system. Time to read the documentation and to integrate everything. And then first, the Java scheduling is handled by the JVM, meaning that when you change your RTOS, you go to Microsoft Windows, you go to Linux, you go to some different kind of RTOS with different scheduling scheme. The scheduling of your Java code will be the same. Meaning that not only it's portable from the binary stuff because you can compile once and run anywhere, but also your scheduling scheme will remain the same, whatever the RTOS architecture. Second thing is you can easily prioritize the Java and the C code, because you got one single task for your Java. So if you say, oh, I got some specific and high priority task for my C code because I've got some timeout for protocol management or whatever, then you can say, okay, my Java code will be in my C task with a very lower priority, and the Java will not preempt any C code because it will change my system. And whatever the number of threads, Java threads, the CPU allocation will be the same for the Java task. And eventually, the system also allows to synchronize or to call C code in a synchronized way or asynchronous way, which is very flexible. Okay, so far? Okay, so now you got your RTOS available. Next thing is to interface your C code. So you have on the left you got the Java code, and you would like to call some kind of C code and get back to the Java world. Usually it's called GNI. GNI is error prone. You have about 50 exceptions if you want to catch everything. And how much time do you need to bring an object to C code? Almost never. You need to pass data, especially in embedded systems. So we provide another API called Simple Native Interface that allows you to call C code and just to pass base type arguments and buffers of base types. This is an example. Here I want to toggle a pin on the microcontroller. So I want just a few lines. Let's go. So you've got your Java code here. I just need to call a toggle method that is implemented in C code, right? So I just say it's native. And while I want to call this every 10 milliseconds, so I just call that method. And in C code, I just include the SNI interface APIs, and I use the same naming convention of my compared to my Java code, and then I just fill in my C code with some C code, right? So it takes 4 lines. You can imagine that the resolution of the symbol is almost link time, meaning there is no overhead. So it's pretty much quick, no copies, no extra buffer required and everything. Very straightforward. In the same way, you can interface data, meaning that you can share a buffer that is at the same place, so that the Java can write in that buffer and the C code can access to that buffer at the same time without duplicating the data. Okay? So this is called an immortal object. Again, here you just declare a set of immortal, and you declare this array, and I declare a native function here, and I call that native method with the reference of the array, and this reference in C code becomes a pointer. Okay, so if you want to share a driver to send bytes over Bluetooth or whatever, this is the kind of things you can use quite easily. We have a second. The problem with SNI is that you might not want to call C because C is not secure. So if you make a mistake when calling C code, then you might have a problem with your system. So sometimes you just want to keep your Java threads running, your C threads running, and just pass messages. And this is why we have the shielded plug system, which is a pub-sub mechanism, where you can publish data, and the methods, the Java methods or the C functions can subscribe to that messaging and get the events and get the data when the data are available. And then it's a spatial and temporal decoupling between the two worlds. I won't get into the details, but basically what you do is to declare your buffer, you use an XML file. Here I declare some wind value, some temperature value. I got my wind object, my wind class, sorry, and then you can use a read object, and here you get the read from the database when it's available. On the C side, very similar. The wind now is, of course, a structure, and then you are able to write some data in the structure, okay? That will be published to the Java world. Very simple, couple of lines, no bloatware. Okay, so once you've got your simulation platform, once you've got your RTOS integrated, you are able to interface to the firmware and so on. Then you can build your simulator. Because the problem in embedded world is that you design an application on a PC that will be executed on some hardware. So your hardware might not be available, and you would like to prototype some software. So you can build your simulator. So we provide, when we provide the Java platform, we provide the embedded Java platform, and we provide a simulated Java platform. And this simulated Java platform can simulate peripherals you might have in the embedded world you don't have on your PC desktop, like, say, a temperature sensor. Okay, so you can modelize with mocks your temperature sensor and then be able to exercise your software and to test it and so on. So here is an example here. I've got my application here. I want to blink a LED. So I called a toggle for my LED, and this toggle is a native. So either because you know you are on the simulation system, you write some toggle in Java, but the code you will be testing is not the actual code that will be embedded in your system, because the toggle is in native in your embedded system. Or you say you use the simulation system, and the simulation system will detect the native call of the Java to the native world, and it will redirect the native call to a mock. And this mock has been declared and developed by yourself here in Java. Okay? Same for LCD. You can use your graphical library, and when we will have to write some pixels, it will write the pixels on the front panel mock. Okay? That's for the JVM integration. So let's have a look now on more Internet of Things system with the second platform, which is hardware as a service system. The integration is similar. It's just the VM is a little bit different, and because we would like to serve some specifics of the IoT market. So here is two examples. The first one is about home automation or home energy management. What you have here is some kind of gateway. Could be your telco provider gateway, but could be a small gateway you provide from your company or your design yourself, and that gateway will be able to manage a couple of bunch of actuators, sensors, anyway, some devices, right? And these devices might come from different providers. And that's a problem. Today in home automation, either you use the same provider for everything, or if you buy from different providers, you're not able to manage, it's like a little bit like your audio system. How many remote commands do you have in hands, right? Same here. So the idea is to be able to allow system providers to download on the hardware gateway services that can deal with their own hardware, and possibly to exchange or to share APIs between different providers. Imagine in the room, I've got two lights, one from provider A, lights from provider B, and I want to bring the two lights on at the same time. Okay? If the gateway, when I enter the room, the gateway detects that I'm entering the room, it can, from the two services, call the right lights to switch them on, right, at the same time. Another idea is about wearable devices. You might use a smartwatch that will deal with your sensors you might have on your clothes, right? So, for instance, you want to interface to Adidas, to Polar, to Nike, and either you have your big cell phone and so on, and maybe you don't want because you are swimming or whatever, so it's not useful. So you might want a small gateway like your smartwatch that will be able to handle a bunch of sensors that comes from different manufacturers. And then you have to allow these manufacturers to be able to download some services dedicated to the sensor management inside the smartwatch, right? So it's a bit like Android, but in more constrained system. And so the problem we have to solve here is energy management. So you can't pile up tons of libraries. You have to be vertically integrated. So small cost-effective environment, small memory footprint. You have to be able to share services between each others to create an ecosystem. Otherwise, if no ecosystem, no business, nothing to provide. This is a problem usually in home automation. You have to guarantee some data reliability and the service management. If you have a service that sucks your power supply, can you stop it? Because it's a hack. And of course, security. Last problem we have to solve is it's a fast-moving market. And today, what's going on in the Internet of Things issue is that you have a bunch and tons of actuators and hardware systems. You have services and people who want to provide services. And they cannot align themselves because if the service depends on the hardware, each time everything is moving, and how to match everything together to make something consistent, it's very difficult. This is why you need some kind of mediation platform or an application platform that is portable, that can fit anywhere, so that platform can interface your hardware and your services. Okay? And this is where we are as a Java platform provider. We provide Java virtual platforms that can fit in a smartwatch, that can fit in a gateway, small gateway, high-end gateways, with the same features. So that's the solution. So you have some existing application here in native. If you look at the gateway, it could be the VOD, could be internet access, could be video streaming and so on. And or on small devices, you also have your C code available, up and running. And then you add a new Java platform that will manage the service on top of it. So let's take it more in the architecture. Just before, why we do this? Okay, here is a story. In France, we are working with a big telco provider, and there are 150 people doing the gateway. They build the gateway from the software point of view. It's quite complex. So you are a marketing guy, you have a brilliant idea, and I want to provide a service in the gateway. And then you have to convince your management, make a business case showing that 100 people will be used 1 month to fork the gateway software, to make a new software, to test it for trial. Okay? So you cannot prototype. Because you cannot prototype, if you provide a small virtual machine that is included in the box and that can run securely a service, then once deployed, you can deploy a service within 1 week without asking anybody. Okay? And then the marketing guy can test new services and make trials. It's like on the GUI, when you're happy to prototype a GUI when you are designing a GUI. Here it's the same. We want to make marketing people able to prototype new services. Of course, you need to build your ecosystem, and then maybe you have 2 services that should not communicate because they are competitors. So you have to protect that. Like Android, you want your customers to choose the functions they want to add to the box after deployment. I mean, your Android or iPhone, it's when we buy it, it's always the same for everybody. Now it's yours because you changed and you customized it. And of course, when you are dealing with gateway providers, usually they have gateways that are in the field for 5 years, 7 years. So if you come up with a solution with 10 megabytes, it won't run on all the boxes. Okay, so you have to find something very small. So here is the architecture. So again, we are based on JVM, and this JVM usually is used in connection with OSGi, which allows some kind of resource management and service lifecycle. And we change the VM to add new features to support the management of these features, like the life cycle, but also the resource allocation, could be the CPU, the memory, and so on. So you've got the JVM, you've got a special feature inside the JVM, which is called the kernel and features, which allows to manage the features on top of this schematic. Then you can use, but it's optional, some kind of service-oriented architecture like OSGi. And on top of it, you will write some Java code that is the application domain kernel that will define the rules. Who talk to who in the service? Which service access to what in terms of communication channels and so on. This part is considered as to be the reliable system. And on top of it, you will define, or you will be able to deploy features which are not reliable or known as to be not reliable because they have been designed by third parties and you don't know how they've been designed or tested. And these features will be able to access to the system, or they will be access to other features only if the application domain kernel says or gives the right rules to do so. Something very important is the features cannot access to the native code. They cannot access to C code. Okay, so they are not able to hack the system. And this can be checked at the download, during the download process. You make checks so that there is no native call. And then you are sure your features are only virtualized by the JVM. So that's some key elements. So the kernel and feature add-on on a JVM is about 20K. So that means when you have, say, a JVM of 30 kilobytes and you want to add the high security system, it's just a JVM of 50 kilobytes. So still can run almost anywhere. Of course, like we saw on the OS RT integration, you can run on any OS. That means the scheduling of the features and so on will be the same, whatever the RTOS, the underlying RTOS in your set-top box or in your system. Regarding the resource management, we can check the CPU and the memory management, meaning that if a feature is suddenly asking a lot of CPU resource or high demand in memory allocation, then the system will be able to kill the feature because it's considered as a virus or something that is not allowed to be executed on the system, otherwise the system would fail. And in the same way, we can manage the resource allocation, we can manage the resource access, and then we can decide which feature can access to the file system, the TCP IP stack, and so on. The way, why you would say, why it's so secure? Why are you sure that this feature would be accessed and so on to that resource and so on? The trick is because the kernel and feature is inside the JVM. When you are able to make your own JVM, that means that you don't have to work around the information you would like to get from the VM, like usually OSGi does. So what we do is, and this is why the kernel and feature is inside the JVM, when the JVM creates an object from a class, from a feature, there is a tag in that object. Okay, because we can garbage and collect also this object. So each object created by features is tagged inside the JVM. And then the resource allocation and the rights for the access is handled based on these tags. Okay, so it's really inside the JVM and you cannot hack it because from the feature side it's only Java, so it's interpreted by the JVM and you can never access to the JVM inside. Last but least, security. You can kill a feature. When I say kill a feature, it's not only the execution. because otherwise you will leave tracks everywhere and data and so on. When we kill a feature, we kill the code, we kill the threads, and we kill the objects and all the data, meaning that nothing remains in memory. It's a pure clean. And of course, there is no backdoor because everything is in the VM, so you cannot implement backdoors to allow some feature to access to strange things. Then, if you use OSGi, if we connect the kernel and feature to OSGi, then the kernel and feature will take care of the bundle life cycle management, okay, like we saw previously for a feature. Again, we provide the resource management. I think it's RFP 200 something, the resource management in OSGi. So you can manage all the CPU and memory allocation. And same for the physical resources access. Then, maybe you know there is big issues in OSGi about isolation. There are lots of tricks to get you are an object, you want access to another object, and of course you can have some tricks to get access to an object you shouldn't have access to. So of course using kernel and feature this is solved. And for unloading and uninstall bundles, you're probably aware about stale references in OSGi. You kill a bundle, and there is another bundle that is linked to that bundle, and the bundle is killed, but you have weak references, and then you think the object is still there, but it's not there, and so on. Okay, OSGi thinks you write good code, and you manage your bundle in the right way. Of course, with kernel feature, because when we remove a bundle, we remove everything. There will no weak references and stale references, and of course no zombie threads at the same time. Okay, so thank you for your attention. If you have any question, please do.
So how small can your VM run? What's the smallest possible configuration?
So the smallest configuration is about, it's usually a Cortex M0 microcontroller. The memory footprint is 256 kilobyte flash, 32 kilobyte RAM, and we have customers making intelligent switch buttons with a square LCD, 128 by 128 pixels. And so when you enter the room, the LCD detects you are in the room, and according to the scenario or the usage, you will have a switch on the light, heat up the heating system or whatever. And this is a $1, $1.50 system. Everything built in Java. So why people are using Java on such small microcontrollers? This is because usually they have some kind of mid-range paradigm. Either they work on a very large system like Linux plus Qt and so on graphical design, and what they've done, they cannot reuse it on mid-range or low-end system. So usually we start with the mid-range system. It's a QVGA color display like a coffee machine and so on. And the guy knows that the same code can be reused on a very low-end system and on a very high-end system, even using Linux. He can reuse all the software code he invested in. And this is why our customers are choosing us. Usually we do some proof of concept to prove that Java, because everybody knows that Java is slow, blah, blah. So we have to prove something sometimes. And usually the proof of concept is we do the same application on Linux, high-end microcontroller, and black and white display. And once he knows that everything runs correctly, then he says, wow. Yes?
So I suppose that when you build your Java machine, you have software to emulate the hardware that may not be there, and you choose at compile time. If you have
On the simulation system?
No, since your virtual machine is flexible,
Yeah.
when you compile it, I suppose you switch on soft floating point, for example, or hard floating point. So you emulate the hardware that's not there?
Yeah, we depending on the hardware that is used or available on the CPU, then we will change the native libraries like floating point unit, for instance. That's your question. If you've got a VPU, for instance, or FPU, we will use the FPU. If there is no FPU, we will have a software FPU like a library, floating point library. Just one thing: the JVM is not Java code compiled into assembly. The JVM that runs in the embedded world is a normal JVM that checks all the runtime exceptions and so on. This is still interpretation also, okay? It's not direct. Everybody knows, everybody can make Java compile to assembly. That's dead easy, okay? You have open source projects in anywhere, that's easy. No, this is the VM here. If you've got an index fault when accessing to an array, you will get an exception. No, no, because, well, that's a good question, JIT. Just-in-time compilation. Okay, JIT is very difficult to make. There are only two companies who have a good JIT, Oracle and IBM, and this depends on the target. For instance, some companies might have on ARM a very nice JIT system because it's the mainstream, and when the customer wants something different, sometimes the speed is divided by 20. Okay, so it's difficult. Android bought a JIT from another company, and on the Android 3 and early 4, they used a JIT to accelerate the execution, and now they are stopping. They stop the JIT feature, and they go back to the AOT, ahead compiling time, because the JIT, it's a huge machine with a large overhead in terms of processing, which is not good for power consumption. So now, if you look at Android, they use ART, which is the Android runtime, I don't remember, which pre-compile or pre-process the bytecode in the JVM, in the Dalvik JVM, to be optimized, and this is what we do. It's IoT. I mean, we take the bytecode from Eclipse, and we, like any VM, we change the bytecode to optimize the execution, because the normal bytecode of a JVM is not done for execution. It's for math first, and for checking. So to get a very standard execution model. But once you want to be executed, you never use a bytecode, because otherwise it's not a good job. So you have to change it, and there are some adaptations. This is IoT. And then you have different strategies, and this is a part of our knowledge. Yeah, I mean, if you use JIT, it's a compiler, so you need 2-3 megabytes more on your target to be able to compile at runtime.
But I've tested the same JVM with just-in-time compilation on and off, and the execution speed is quite...
That depends on the hardware target. That also depends on the price. I mean, if you look at pure performance, sometimes JIT is faster. But now, if you compare the performance ratio with the price of your bill of material, then JIT is very, very low in terms of performance. That's always a trade-off. You know, embedded system is a trade-off area. Yeah. Yes? Yes. Of course, you can obfuscate your bytecode, right? Because we make our JVM, we can rework the bytecode that is executed in the embedded world. Meaning, for instance, if your company needs a special encryption for the bytecode, we can make a JVM that has its own bytecode encoding. Okay, so your company will have a special JVM with a certain bytecode combination, meaning that anybody that does not have the pre-compiling or optimization system, they will not be able to download some Java code from outside without your special tools. So instead of, again, it's like vertical integration. Instead of putting things on top of it to try to protect the JVM. We change the JVM and we take the root cause, by code execution encrypted. Okay, it's very easy for us. We did that several times, especially in your area. I think we met yesterday. Any more questions? Okay, so thank you very much. Thank you.